Welcome to this executive masterclass on industrial sector decarbonization. We will focus on heavy industry CCUS integration, specifically within the cement, steel, refining, and petrochemical sectors. Prepared by Dr. Qureshi from National University of Singapore. In this video, we will deconstruct process and combustion emissions, evaluate advanced integration technologies, and analyze the techno-economics and regulatory landscape for industrial decarbonization. Decarbonizing heavy industrial sectors is a complex challenge that requires tailored strategies for each unique process. Emissions in heavy industry are split between combustion, accounting for about 35%, and inherent process emissions, which account for about 65%. CCUS is the primary solution for process-related emissions. Heavy industry contributes roughly 30% of global greenhouse gas emissions, representing approximately 10 gigatons of CO2 per year. Large-scale CCUS deployment is critical to reach net zero goals. Let's explore CCUS in the cement and lime industry, focusing on the chemistry of calcination and direct separation technologies. Cement production requires thermally decomposing limestone at 900 degrees Celsius. This chemical reaction is responsible for up to 65% of a plant's total emissions. Capture configurations for cement kilns include post-combustion solvent capture, which treats flue gas, and oxy-fuel calcination, which concentrates the exhaust stream to lower capture costs. The LEILAC direct separation technology uses indirect heating to isolate calcination gases, producing a high-purity CO2 stream without chemical solvents, and offers scalable integration for existing brownfield sites. This matrix illustrates that direct separation technologies can significantly reduce the levelized cost of capture compared to traditional flue gas scrubbing methods. We now examine iron and steel industry decarbonization, comparing BF-BOF routes with direct reduced iron, or DRI, pathways. The BF-BOF process relies on coke as a reducing agent. Decarbonizing this path is complicated by the variety of gases produced, which have low CO2 concentrations and variable pressures. DRI CCUS technology offers a near-term transition bridge, providing 80% emissions reductions at a much lower capital intensity than a complete shift to green hydrogen. Top gas recycling for blast furnaces improves efficiency through gas separation, tuyeria reinjection, and oxyblowing, which together eliminate nitrogen dilution for better CO2 capture. This table summarizes various steel decarbonization pathways, showing their abatement potential, current technology readiness levels, and relative capital expenditure requirements. We are now shifting our focus to the refining and petrochemical sector. We will explore how FCC unit emissions and multi-stack integration are critical for successful carbon capture. Refineries present complex challenges for CCUS due to their dispersed emission sources, the difficulty of consolidating low-pressure flue gases, and the severe lack of available plot space in existing brownfield sites. High-priority targets include fluid catalytic crackers, which produce significant CO2 concentrations, and steam methane reformers, where high-purity syngas streams allow for cost-effective capture. In petrochemical facilities, we look at steam cracking furnaces for fuel switching and ethylene oxide synthesis, which offers low-hanging opportunities for CO2 capture, along with the electrical upgrades required for compression. Implementing CCUS can increase steam demand by up to 35%. This requires proactive management, often through combined heat and power units, to ensure refinery operations remain stable. Next, we will examine the chemical and fertilizer industries, specifically focusing on the decarbonization of ammonia and urea production loops. Ammonia synthesis generates processed CO2 as a byproduct. While some is utilized in urea production, the remaining volume requires permanent geological storage to meet full decarbonization standards. Ammonia and syngas plants are ideal for low-cost capture. Because these processes already involve high-pressure purification, CO2 is easily separated, keeping compression costs at a minimum. Industrial cluster symbiosis is key. Sharing waste heat and consolidated compression infrastructure across different plants significantly improves project bankability and reduces overall transport and storage fees. In this final section, we will discuss the techno-economics, the impact of the carbon border adjustment mechanism, and the steps required to execute these projects. This cost of abatement curve highlights how process gas concentration and site-specific factors determine which projects achieve financial viability first. The European CBAM tariff creates a powerful incentive. By deploying CCUS, producers avoid penalties on imports, effectively protecting their competitive edge in premium export markets. Retrofitting existing brownfield facilities requires careful engineering. Navigating physical constraints is as important as selecting the right capture technology. To reach a final investment decision, projects must secure bankable offtake agreements, guarantee engineering performance through EPC contracts, and solidify policy monetization strategies. Thank you for completing this module on industrial decarbonization. Review the references provided to deepen your understanding of these critical technologies and regulatory frameworks. If you are interested in exploring consulting, collaborative research, or professional training related to these industrial decarbonization strategies, feel free to reach out using the contact information provided on this screen.